Our PCST sir has joined. I welcome our PCST sir for this webinar. I also welcome Mr. and his team for this webinar, and a warm welcome to all the participants. Sir, would you like to say something? Sir, your
CST sir, good afternoon, CST sir.
Okay, good morning, everybody.
Sir.
To all participants, I just want to highlight only one point. Because see, LTE is the technology of today, and as far as railway is concerned, it is a technology for tomorrow as well. Right now, we had GSMR only in the Grand Court section, and perhaps that was also not utilized very well. But now we are going for train collision avoidance system and so many other things. So all these applications and remote diagnostic, so many artificial intelligence and machine learning applications we are going for. So all these things are very high speed data transmission, and for that dedicated LTE network is very much required. So this webinar has been arranged so that we have a acquaintance with this LTE technology, and people from Nokia who has been doing our GSMR maintenance work and other things. So they are the most suited to give us the exposure to LTE. So I think all participants will get benefited by exposure and acquaintance with this LTE technology. So I will request you to go ahead with your presentation.
But sir, you please take over.
Thank you, sir. Thank you. Good morning to good morning, everyone. I will request everybody to keep the mic on mute. Thank you. So warm welcome and thank you very much for giving us the opportunity to present our new technology LTE for the Indian Railways in the ECR section. These similar webinars were also been conducted in the zonal railways. So me along with I am SN Bhatt. I am heading the sales in Nokia based out of Gurgaon. I am already interacting with the railways and other zonal railways. I am already aware of the lot of people, I think, in the ECR as well. So we interacted earlier on the GSM topic. So along with me, Mahipal is there. I will Mahipal is heading our technical solution. I will just request Mahipal also just introduce himself. Mahipal.
Hi everyone, Mahipal this side. As Bhatt Saab has mentioned, like I am heading the technical solutions for Enterprise India department. And in this presentation, basically, we will cover two topics. Like first is about Nokia, what is Nokia and our presence in India. And second is about the basic concept or, concept of LTE. So Bhatt Saab, over to you.
Yeah, thank you, Mahipal. So, sir, we have a presentation in the two sections. The first section is around 10-15 minutes just to run through the what is the Nokia's activities globally and also in India and specific to the Indian Railways, what is we have done and what is our capabilities and the structure here. While I think most of us, I think we may be aware of the Nokia's presence here in India. And the second section is the completely the technical section of the LTE, where LTE, we will cover the LTE architecture and then how the LTE has been evolved from the 2G, 3G, 4G, what is the 3GPP standards, and then what is the architecture of the LTE and the main elements or the blocking elements or the block units of the under the sub elements of the LTE and how it is interconnected and how in the railway scenario, both for the ETCS2 and TCAS solution, how the LTE can be used and some applications and something on the network planning and what is the requirement on the radio side. So this is what we are going to cover. So we will have around 1 hour of presentation and request everyone to raise or the queries during the technical presentation, or we can write in the chat box as well. So Nokia, as you are aware, is already implementing a lot of the 4G network from last many years all over in the world. So we are #1 in the 4G radio, and we are in the copper access, we are in the edge routing, we are in the services and in the software. So we are basically mainly a telecom company. So where telecom is started with the 2G, 3G, 4G. So now we are also talking about the 5G. So we are basically based out of in many of the countries. So we are headquartered right now in the MNC, in this type of companies. There is no the one headquarter. So we have the multiple offices all over the world, and some of the leading units are in the different countries. So it is no, it's a Finnish company, but otherwise we have the offices all over the world. Specific to Nokia in India, so we are having a headquarter, the main sales office in Gurgaon, which is very next to the Delhi, and we have the other sales office in Mumbai, and we have the multiple offices in India. So the main two offices are in Mumbai and Delhi, while because many of the operators are operating from either from Delhi or Mumbai. So the customers who are having the headquarters or the main offices in Delhi, like the MTNL, BSNL, Indian Railways, and then Airtel, Bharti Airtel is based out of Delhi. But the Reliance, then the Reliance Jio, and the Vodafone Idea is based out of Mumbai. That's why we have another office, big office in Mumbai. So we have more than 16,000 employees within India, which is almost 20-25% of the overall Nokia strength. We have the global NOC, that is which is a network operation center, one in Chennai, one in Noida, which are interconnected, and we are doing a lot of the managed services for these telecom operators. The telecom operators, they normally do outsource the complete services business and the maintenance of their network to the OEMs. So we are maintaining their network on behalf of the Bharti Airtel or with Vodafone or with Reliance for their network. We have the software development center in Bangalore. So we have the global R&D center for the complete Nokia's their software is being developed in Bangalore. We have a manufacturing unit in Chennai. So the Chennai where the earlier SEZ was there, the same place. So a lot of our radio equipments are being manufactured within India, and we are making in India, and also we are manufacturing all these radios which are being delivered to the private operators like Bharti Airtel, Vodafone, Reliance from Chennai factory, and we are also exporting to the other countries. The Chennai factory is one of the Nokia's main factories, is producing all the 4G and 5G radios these days. We have a global delivery center in Noida, where we are having a centralized bid preparation center. Wherever there is some of the global tenders are coming up, whether it is in India or outside India. So we have the resources in Noida where they prepare the bid preparation, all the documentation, everything, solution is being prepared in the office in Noida. So in India is being used a lot of the technical manpowers, the services are being used from India, and India is one of the main, is the market for the Nokia's, the resources. So as I mentioned, so we are presence in all the mobile operators. We have the core access, the core networks. We have the managed services, because as I mentioned, so we are doing a lot of the managed services for all the operators, wherein this network operation center and the other the maintenance staff is being directed from the network operation center and the main management system, and generating the reports, KPIs for all these operators is being generated from this NOC. We have number one position in the optic market, where the IP MPLS DWDMs were being deployed. So we have acquired Alcatel-Lucent earlier in 2013, and then afterwards all these Alcatel products are now part of Nokia. So we have the IP portfolios, the L2, L3 switches, and the DWDM optics, all this which were part of earlier Alcatel's product, Alcatel-Lucent product. These are all now part of Nokia. As you are aware, we have already deployed a transport GSMR under the transport segment under the Indian Railways. We have deployed more than 3,500 kilometers of the GSMR within India, and we are having a major market share in Indian Railways GSMR network. I will just skip this one. So as I mentioned, so Nokia is currently having the product portfolios from earlier Siemens portion, earlier Motorola's portion, and Alcatel-Lucent. So the Motorola's radios were also been acquired by Nokia Siemens. So as you are aware, initially it was Nokia and Siemens were different companies. the Siemens portion of the, and Nokia made a Nokia Siemens as a 50-50 joint venture in 2013, and then they had to run around 5 years with the Nokia Siemens, and then Siemens exited from this joint venture. Then the 50% of the Siemens has been acquired by Nokia itself, and it made a 100% Nokia company. So in the meantime, we acquired Alcatel-Lucent and also the Motorola products, and these are all now part of the Nokia's portfolio. We have a big factory in Chennai, as I mentioned. So we are already deployed more than 4 million of the radio products from Chennai factory, and our Chennai, sorry, please. Hello, sorry. So our Chennai factory is completely automated factory. So we have converted all the network within the Chennai factory based with the collaboration with one of the operators into Industry 4.0, and we have converted taken out all the cabling, everything, and it's completely 4G and LTE based network we have used for the manufacturing and automizing the complete the factories. So we are majorly right now is producing both the 4G, 5G radios from Chennai factory. So as you are aware, this is the major the GSMR network within India, mostly within the northern part of India. So we have the GSMR from Jammu up to Ghaziabad up to Calcutta, and here in the NFR and ECR we have this Dhanbad Mughalsarai section, and we have the eastern dedicated freight corridor which is running parallel to the Ghaziabad Mughalsarai section, and there is a western corridor which is being deployed from the Delhi to Mumbai, and the other networks from the up to Jhansi. So as I mentioned, so it's almost 3,400 kilometers of the GSMR deployed in the different zones. We have deployed the contracts, the Indian Railways contract directly and also through our partners. So like the signaling partners like Alstom, Ansaldo, Siemens. So we are also worked with them as a part of their signaling package. So we have the experience of both the public network and also the railway network. Since we are already deploying the LTE from last many years for all these private operators, so we have the experience of the public network. What is the requirement in the public network? Since we have deployed all the railway specific critical, the safety network, mission critical safety network like this MTRC and GSMR, we know what are the requirements of the railway segment as well. So we have the strong presence in India. We have both the experience of the private network and also the public network tendering process, and also because most of these railways and the government tenders require long-term support. So we are present in India from last many years, and it's going to be here. So we are the long-term partners for the Indian Railways. So this is one of the single line diagram which showing from the GSMR from Jammu Tawi up to the Dhanbad section. So this is after Dhanbad to the Calcutta, which is in the Eastern Railway. So this black portion or the blue portion is Indian Railways network, and this orange portion is the DFCC network, where only in the detour they are putting the radios. So it is mainly almost 90% of the radio network of the Indian Railway is being used by the DFCC. Only in the detour portion the new radio network is being deployed. These are the list of few projects which we have already executed. The NCR is around 420 kilometers. NR there is 850 kilometers. NFR there is around 650, 670 kilometers. And ECR you are aware that is from Pradhan Kumta to Mughalsarai, which we already operational and we are doing already the AMC for this portion. NCR which is already now executed for this section, and there are other sections like even in the Metro Railway Calcutta, we have implemented the GSMR through the leaky cable. All the old this Metro Railway Calcutta, where there is underground trains are being running, it's been completely covered with the GSMR with the help of the leaky cable. So the EDFC, where we are doing the Alstom, is the front-ending contractor. So we are working as a subcontractor to Alstom for the GSMR portion. So this is just an overview of the Nokia's activities in India and Indian Railways. So I will be happy to address any other queries in the later. So I will hand over to Mahipal to take over from the technical section.
Yeah, thanks. What's up? So I will just take you through the technical, basic concept of LTE. So I will try to cover as much as basic possible. But however, if you have any questions in between, please don't hesitate to interrupt me. As Bhatt sir mentioned, we have deployed GSMR in India. Also recently, we participated in few tenders, couple of tenders floated by our Railten and NCRTC. So NCRTC, we won that project. That is basically ETCS level 2 is deployed for signaling along with the LTE. So preliminary design has already been approved. Now detailed work on detailed design is going on. So this is luckily it's in the part deploying the first LTE network for railways in India. From India, we also supplying this network to Dhaka Metro. Also, this is one of our project where it's also in implementation stage, and today they have just tested their first train run basically. So that is also one of a prestigious project for Nokia India. So I will just take you to through the LTE basically. So LTE standards, basically LTE is an open technology. In today's today everyone, like all of us, are basically using this LTE. This is long-term evolution. Another term we also called it 4G, the fourth generation of mobile basically. So all the operators in India, if you talk about Airtel, Vodafone, BSNL, they have deployed a fourth generation of network, and we are using fourth generation of services using these networks. So EPC is basically evolved packet core. So in LTE, the architecture is very simple. It consists of two parts. One is the RF radiating part, that is E node B, and second is the EPC, that is the core part, that evolved packet core we called it. And EUTRA is basically evolved universal terrestrial radio access technology, that is the RF protocol. So totally EPC plus EUTRAN become the EPS, that is evolved packet system. So that is your LTE network you called it, or you can even call it a 4G network also. So that EPS is equivalent to EPC, that is core, plus your E node B, or BTS in GSMR we call it BTS, the RF part basically. So this is based on a open standards, and 3GPP is the body, that is third generation partnership project. This body was established in 1998. So this body basically published the standards for all the mobile technologies, whether it's 2G, 3G, 4G, all these standards are published by this 3GPP body. And 3GPP body, every year they publish the standards. Currently, December 2020, they published the release 16 for LTE. So this everything was started from release 1. So release 1 was kind of a 2G or second generation of mobile, and later on, like 2.5G was there, that we called it GPRS also, and then Edge was there, enhanced data radio, GPRS. All these are there, and then 3G was introduced. 3G was introduced in release 5 basically. So release 4, sorry. So release 4, 3G was introduced, and from release 8 LTE was introduced. So today we are sitting on release 16, 3GPP release 16, and this release 16 is consist of your LTE or 4G, as well as 5G was introduced in release 15 also. So this release 16, the standards basically consist of all your from release 8 the 4G standards, plus all the evolvement from release 8 to release 15 in LTE. So whatever are the requirements, those are part of these releases, as well as 5G was there in release 15. So you can say who are the participants in 3GPP? Basically, all the cellular operators are there. From India side, you can say Airtel, Bharti, or Vodafone, BSNL, and OEM manufacturers like Nokia, Samsung, Ericsson, Huawei. All these are the manufacturers, plus the software developers and chip makers like Qualcomm or Huawei. All these are part of the 3GPP body. Whoever is manufacturers or contribute to the mobile cellular technology. So the interesting part is release 8, long-term evolution, LTE and 4G was introduced. However, from release 12, 3GPP also introduced the public safety features. When I'm saying public safety features, this network can be used for the first responders or for the emergency situations or public safety usage. So in this, what they actually introduced, what are the features required for the public safety, like one-to-many call, We called it group call also. We right now we are using walkie-talkie for the same, and some advanced technologies like Tetra or APCO. One-to-many call. Similarly, one-to-many video calls are there, and proximity services like device-to-device communication. And these features are there. However, these features are with certain quality of services. So the quality of service for the first responders are very stringent. So all OEMs, whoever is providing these services or providing these features, they need to comply with that quality of standards or services basically. What's up? Next slide. So this is more about how the technologies evolved from 2G to 3G, 4G, and 5G. So if you see 2G, I will just give you a basic difference here. So second generation of mobile, we call it GSM also, Global System for Mobile Communication. That is TDMA based technology introduced in 1991. So that is access is basically totally based on circuit switch. So that is more, you can say, inclined or towards voice. So there was a data that is very, very less. So when it was introduced, the data speed was 4.6. Later, it was the maximum data speed we got it 9.2 kbps. And with the introduction of 2.5G, we got the maximum data speed, GPRS, we call it, and then edge 64 kb. That was the maximum data throughput speed we got it from the GSM technology. When this 3G was introduced, now 2G also, you see GPRS is basically general packet radio services. In this, the packet switch was introduced in 2.5G or GPRS. Now, when 3G was introduced, 3G is also called as UMTS. And in this 3GP, there were further release 4 to release 7. The 3G was there. So circuit switch was there as well as packet switch are there. So packets, the voice is based on circuit switch, whereas the data application are based on the packet switch. So for voice and the backward compatibility, we uses the IMS, that is integrated multimedia services for all the IP backbone. Now release 8 onwards, LTE was introduced. So LTE is basically 100% IP technology. You see there is no circuit switch, voice or something. Everything is on packet. Now it's 100% IP, and all the applications, these are connected through the IP. So IMS is only used for the backward compatibility for the 3G, 2G as well as the PSTN, where you need are based on the old technologies. So for those voice communication. Otherwise, it's 100%. You can say 100% IP technology. Now, the major difference between this is LTE is basically end-to-end, it's 100% IP. The quality of service, the QoS basically is also you can define from end-to-end, from packet when it's originated from its origin and then to the termination point. So for this point from pick point as well as to the delivery point, you can define the QoS. So you have 100% control on that. Third major benefit of LTE over other technology is the low latency. So GSM, we sometimes call the latency is around more than 100 plus milliseconds, 150 or 200 milliseconds also for one way. Whereas the same is greater than 50 milliseconds in 3G. However, in LTE, this latency is less than 10 milliseconds for both ways. So one way you can say if something for uplink, it's around 5 milliseconds, you can say. Mobility is there. So other major benefit is high bandwidth. So from 2G, as I told, like data speed was maximum 9.6 kbps, whereas in 3G the data speed was maximum when it was introduced is 384 kbps. Later on, we reach out to the maximum of in downlink for 5 kbps, that is in release 7 with the HSUPA, HSTPA. So 5 Mbps was the maximum throughput we achieved through and with the introduction of MIMO also. These are the different features and technologies which actually help to get a higher throughput or data speed. So 3G maximum data speed 5 Mbps uplink and 11 Mbps downlink was the maximum throughput in release 7 of 3G. Whereas in release 8, when LTE was introduced, this was the minimum throughput we got. Now with the MIMO and with other features, release 9, 10, the data speed right now we got it around 1 GB also. But yes, all these things depend upon the frequency bandwidth and other RF aspects also. But yes, 1 GB of throughput is possible in LTE with release 15 and above. We call it 4.9G also in other terms. The major other benefit is like it's a backward compatible, as well as you can evolve, or the evolution to the 5G path is also ready. So there's the same equipment, the same standards. You can upgrade your equipment to the 5G if like certain basic requirements are meeting. Now, public safety releases I mentioned, which is more critical to the railways or for any first responders or public safety networks. So in release 8 to 10, you see there are basic few features like voice over LTE is there, quality of service, ciphering, high speed train support up to 350 kilometers. So all these are there. Yes, to 10. Well as release 12, the group communication public safety features of group communication, features like preemption, features like proximity services is nothing, it's a device to device communication, and mission critical QoS calls QCIs. Basically QCIs is nothing, it's a QoS, quality of service call identifiers. So for each packet you assign certain call identifiers or quality of service so that it can meet minimum that service, that packet basically meet minimum that service. So these kind of features are there for the public safety releases or public safety data. Similarly, release 13 and 14, the mission critical video was also introduced. Because of high availability of video or data throughput, you can make a video calls also. And this is not one-to-one video calls. You can make a one-to-many video calls. Similarly, like in a walkie-talkie, one person presses a PTT button, and all other radios which are in the vicinity of that particular radio are able to talk to, or you can say part of the communication. So in this, what happened in this technology, you can make that one-to-many call similar to walkie-talkie, as well as one-to-many video call also. You can press a video call and make a video call to a particular group also. You can form a group and to all the members also, or a broadcaster sector. So these features are there, and these calls, they have a very high quality of services. Like the call setup time in normal uh, GSMR or an LTE also, sometimes we make a call private call also. That private call, it takes, sometimes it's take few seconds also for establishment, and sometimes it's happened in a few milliseconds also. So all these things are there. Whereas for public safety, the call will be established in 300 milliseconds, less than 300 milliseconds always. So these kind of quality of services are defined for public safety features. So it will not take more than 300 milliseconds. So you presses your PTT and the call will be established within no time. And IRENE, I hope you are aware of IRENE. IRENE standards are basically specifically for railway functions, and these all European installations or deployments, they follow the IRENE standards. Similarly, for Indian GSMR also, they followed the IRENE standards. So IRENE was more or aligned to the GSMR. However, those are the features and the functionalities which are very critical for the railway operational and functional requirement. Now, in LT, we call it FRMCS. FRMCS is Future Railway Mobile Communication System. So this Future Railway Mobile Communication System is nothing. It adapted the IRENE features or standards basically, and implement and make it a part of the 3GPP standards. It was supposed to publish in release 15. However, it is delayed. It is not even published in release 16 also. The final draft is completed. In fact, final remarks from all the participants is already done. There's a meeting happened for FRMCS in coming month in July. Also, there is going to be a final meeting, you can say. So maybe by end of this year, release 17, there may be this standards for FRMCS are going to be published. So these standards basically, they contain all the features, the functionals, how we will employ or deploy the LTE network or the 5G, etc. for the railway, operational and functional requirement. What's our next slide, please? Next slide. So in this, I will just cover the EPC architecture. So EPC or LTE architecture, it become very simpler from GSMR and 3G. GSMR, for a normal network, you need a MSC or a core, which should be like there are multiple cabinets or multiple racks are required for just one small network. A room of, you can say, 15 by 15 feet of size is required, where you have almost 7-8 racks where you will just deploy the core part. whereas for ion and other packet etc, you need a different racks and different rooms. For E node B also, E node B is nothing, it's BTS in GSMR, so base transceiver station. That is basically size of a 300-liter fridge that time. It's size of that. So it's a 300-liter almirah. You can say in that you have multiple modules and different transceivers, power amplifiers, and duplexers, combiners, etc. So it was huge. The form factor of GSMR and 3G was huge. Plus the architecture also, from BTS, you required a base station controller. So multiple BTS are basically connected to one base station controller, and base station controller further connected to the switch or MSC we called it. So whereas in LT, this architecture become much simpler. So we don't require any base station controller here. So BSC is kind of eliminated in this architecture. So BTS is exchanged by it's a nomenclature change basically. So now we call it enhanced node B. So this is their E node B, that is basically equivalent to BTS, whereas EPC is equivalent to your MSC in GSMR. So this is a nomenclature change, and only these two elements are required. So EPC at the core at a central location, whereas E node Bs are required at the remote locations or the track side or wayside equipment, you can call it. So these are basically providing the coverage. So in this slide, you see the gray part. These are basically the main equipment or main modules of RF. Main module of EPC, you can say EPSC in fact. So this E node B, basically there's a cloud type bubble is here at the bottom of the slide. So this is nothing, it's basically the RF coverage or the RF signals that is generated by this E node B. So E node B is responsible for transmitting the RF signal or RF coverage. So from here, this E node B is connected back to the EPC. Now, all above modules like MME, serving gateway, PDN gateway, is PDN GW, PCRF, and HSS. These are the part of EPCs basically. They have a different functionalities, but yes, they are basically located or placed at a single location, a common location. Whereas E node Bs are multiple in nature, like there are multiple E node Bs based upon the coverage area requirement or the throughput requirement, and these are placed or located at the track side. And this EPC is located at some central location. Now these are the different modules like HSS. HSS is basically the database. So database center, all your database, the subscriber database, identification handlings or authentication keys, etc., are basically residing in this HSS. This HSS is connected to the MME. Right? This is part of MME. MME is mobile mobility entity. So this mobile mobility entity is responsible for the mobility of a subscriber or a SIM or device, you can say. So all the NAS signaling, authentication of a user. Suppose any user, I make a call. Whenever I make a call using my handset device, first this is authenticated by the MME. MME authenticated, okay, this is a valid user, and then further they will allow my call to happen. So these kind of things are are the functionalities of MME. Bearer management. Bearer is basically the packet which comes. Signaling part, basically, you can say. So there are two planes: control plane, that is the signaling part. Second is the user plane, that is the traffic data. So control plane from the E node B is always go to the MME and HSS, whereas the user plane, the bearer, the data basically comes to the serving gateway. So this serving gateway, we also call it S gateway. So MME authenticate the user, everything happened, okay, this is a valid user, and then the bearer goes to the serving gateway. All E node B's user plane or user data, traffic data always terminate at the serving gateway. Control data, signaling information always terminate at the MME. Now this serving gateway, what this serving gateway do? It assesses, okay, this is the data, this is the bearer, I received it. Then MME through this S11 interface you are seeing here, this S11 interface, this MME inform, okay, this particular data you received it, this is intended for the same network or this is intended for the outer network. When I'm saying outer, the same network means all the E node Bs which are part of this same network. Let's assume, I will just give you an operator example. A circle. let's assume Bihar is a circle. So Bihar is one telecom circle. So in this telecom circle, you have one MME, one serving gateway, one PDN gateway, and multiple eNodeBs scattered along the all Bihar plus HSS and PCRF are there. This is single one. Now, suppose a Vodafone network is there in this Bihar. A Vodafone user make a call. So this user when make a call, this MME authenticate this call and said, okay, this call is intended for another Vodafone user. So when this is intended for another Vodafone user, so what happened? This serving gateway send back that info, from the MME, take that information and send the call, or you can say establish that call to the user which is in the other eNodeB or in the same eNodeB. He can be anywhere in the network, but the call will not go out of the system, out of this network. Like from serving gateway, it will come back to the eNodeB. So this decision and everything will happen in the same, these four modules, you can say HSS, MME, serving gateway, and eNodeB, if the call is in the same network. Now let's assume if call is for the Airtel network. When I am saying a Vodafone user originated a call or initiate a call that is intended for Airtel for the any that user can be anywhere in the world. So what happened in that condition? That data will from serving gateway will go to the packet data PDN gateway. So packet data gateway. So this packet data gateway, the role of this packet data gateway is this is connected to the external world. External world, when I'm saying like which are outside our network or this network. So all the allocation of IP address or the data intended for the outside, the packet routing, etc., is taken care by this packet packet data gateway. And also the lawful intercept. When I'm saying if you want to intercept this, so this is all happen through this packet data gateway. And policy enforcement of the data is also happen at this point. So when I'm saying policy enforcement, so this policy enforcement is basically the function of this module PCRF. So this PCRF is nothing, it's a policy charging rule function. So this policy charging rule function, basically all the policies of all the users are defined in this module basically. So policies are basically how you will treat that particular user, how will you treat the packet that is coming from that particular user. For example, I'm just giving you an example here. For a prepaid user, what they will do, they just recharge their mobile. When they recharge with a certain policies, or they buy a pack basically. Suppose I am a user and I buy a pack, or I bought a pack of 1 GB data per day. 1 GB data per day. If I use that or consume that 1 GB data, I will get a throughput of 2 Mbps. If my 1 GB of data exhaust within that 24-hour or prior to that 24-hour, my throughput from 2 Mbps, it will reduce to the 512 kbps. So these kind of policies are there. So these policies are defined in this PCRF. So as soon as I consume my 1 Gbps of data, my throughput from 2 Mbps, it will decrease to the 512 kbps. So this policy basically enforced by on packet data, that the packet when it reaches to the packet data gateway, enforced here by the PCRF. So whenever packet reaches here, the PCRF says, okay, this is from this particular user, he consumed the 1 GB of data. Now this packet will have a throughput of 512 kbps instead of 2 Mbps. So these kind of policies are there, and these are defined for each and every user, and defined as per the not only for users. This is basically users on the bearer, basically on the packet. So each packet will be treated as per the PCRF policies. Now from here, it's a connectivity to the external world. So external world, like I just gave you example of voice service, whereas you can have like all the data services. External IP networks, like all your application servers, like for shopping we are using different applications like Amazon, Flipkart, or Myntra and other applications. Whereas for voice we are using, or video calls we are using, like chatting, WhatsApp we are using. There are other applications we are using like Snapchat or other Instagram, etc., Facebook. All these are different applications basically. So their application servers, they reside somewhere in the external IP network. So packet data, whenever there's a call originated, whether it's a data call or it's a packet call, all this is basically from packet data gateway. The data will reaches to those respective application servers or respective network from packet data gateway and vice versa. So this is a basic architecture of the LTE, you can say, how it functions and what are the different modules. So for EPC, a core part, HSS, MME, serving gateway, PDN gateway, and PCRF. These are the major modules, and eNode B is responsible for the RF generation or RF, signal. This eNode B is connected to the EPC through an optical fiber. Also, you can connect it to the optical fiber or microwave or through satellite. Also, depend upon the different various IP, MPLS, etc. Depend upon different backbone technologies available. But sir, next slide, please. But sir, next slide. What's up? Can you hear me? It's okay. It's coming. I think maybe I am experiencing a network delay here. The same slide come. So slide is not moving. Same slide. I am only able to see the same slide.
Is it moving? No.
No.
Hello?
Yeah, I am able to see the same slide. So what
no, it is not. It is stuck. It is stuck. Something has happened. I don't know. Let me 1 minute.
Okay.
It's not moving.
In the meantime, Mahipal, all the elements are where they are located. They are located in the eNode B only, or where?
Which elements are you talking about?
This SS and MME and all this PDN network.
Okay. No, sir. So eNode B is basically it's a BTS, that is a base transceiver station which generates the RF. So this BTS is there. You can say below the tower or near the tower. You can say.
Okay.
So tower, when you are saying yes, it's connected to the antenna. So this is your remote element, eNode B. Whereas the other modules, they are going to be placed at some central location. So in one room, anywhere in one rack. So MME, like these are going to be in a server basically. So these are the software modules: MME, HSS, S gateway, packet data gateway, and PCRF. So all these are the software which are going to be in a server. So maybe one rack or two rack is required based on the capacity. So we can dimension it as per the capacity requirements. And these are connected through the optical fiber to the remote eNode B. So eNode B, as I mentioned, this is depend upon the coverage requirement or throughput requirement. So we plan and do a RF simulation on the tool and identify the numbers of eNode Bs and then connect it back to the central core. So this is more about the same architecture is there, but here the emphasis on the basically interfaces or logical interfaces connected to each other. So eNode B is also, these are connected to each other. So inter eNode B handover, etc. We call it X2 interface. So these are the different interfaces, like S11 is between MME and S gateway, and S5 oblique S8 between S and P. So this already I think covered. So WhatsApp, you can go to the next slide. This slide basically is on the PDN connection and carriers, how the PDN connection happened. So left side you see this is the terminal, the mobile device, whereas the extreme right side you will see this is an application server. So how this connection happens? Suppose this terminal initiated a call or a session. So this session, what happened? There's a tunnel formed. From the tunnel, first it formed between a terminal to the packet data gateway. So this is a PDN connection. This tunnel happens. Now this is basically based on GTP tunnel. So our dedicated path is or dedicated tunnel is allocated to that particular user based on the QCIs. So every packet or every data will have a certain QCIs, whatever you define that as per the defined in the PCRF as well as in the system. So that particular packet will have that QCIs. Now that is connected to the external world through the SGI interface. So SGI is nothing; it's a standard interface which is a connection to the all the external applications. So this application server can be anything. This can be like you can customize it, you can develop your own applications based on your requirement and put your application server or applications on the in fact near to EPC or in the same room EPC also. As well as you can use other applications which are already existing like WhatsApp, etc. if you want to use. So you just need an internet connection and you can use on your handset devices, etc. also. So all these kind of different possibilities are there. What's up? Next slide. So this is again the same thing how this happened. So first part on the UE, basically this is user equipment. So this is stack up bearer stack up. So from UE to application pair entity, you will see this is end-to-end service. How this is defined? So EPS bearer is from UE to the packet gateway. So this tunnel is the second tunnel you see in the second one. This is basically to the packet gateway. So here we have the control. Whereas on the application pair entity, this is an external bearer. Like maybe you are using internet here, or maybe some external, network. So this part we don't have a control. We have only control on the EPCS bearer when it is inside our network. So like in if ECR is going to deploy LT network, so this is going to be a captive kind of network. So they have full control from UE to the packet gateway. Whatever the communication happened within the network, they have 100% control. So further divided, so this is like a radio bearer, so that is on the radio interface, E-tran you can say. Now E node B to S gateway, this is S1 bearer, and then S5 packet S gateway to packet gateway is S5 S8 bearer. So these are the interfaces basically. So all this we have 100% control. So when the U is ideal, so we will simply release this bearer like as per the situation we have, like whenever we have to make the bearer attachments, we always do, and whenever there's a no call is happening, it's in idle stage, we will just occupy the minimum resources required so that we will give a maximum efficiency of the spectrum. What's our next slide, please? So this is again the same on the protocol level. I think you can pass this. This is more technical, I can say. What's the next slide, please? Yes. So this is about the voice call flow, how it's happened in a system. So just for your information, LTE network will not provide any voice, or any other services. It's basically a pipe, a broadband pipe, or that provides a high bandwidth of data. That's it. So you have a pipe, one end the data enters, another end the data exit, and a vice versa. But yes, this is a very broad pipe so that you will have a higher throughput. Now from this pipe, if you want to send a data, if you want to collect a data, there's a architecture is required. We call it application server at one end and application client at one end. So in other terms, like let's take example of WhatsApp. So in our mobile, we have a WhatsApp client installed in our mobile. So this is a WhatsApp client. So this is an application client. Whereas application server, it will be hosted or located somewhere in other country or maybe. And the communication is happening through the multiple networks. One is definitely the SIM provider or the operator you are using. Second is the IP internet, you can say. And other ways also, like if you're only using internet or Wi-Fi, also through that you are just reaching out to the application server. But so in between, everything is media. From your application client, you are using the media to reach out to the application server and vice versa. So this media is basically nothing. It's here what we are providing a dedicated media, that is LTE network. So, but yes, for the communication you required LTE client, or sorry, application client on your handset or endpoint, and application server on the other part of the other exit of the pipe basically. So in this what we are using for the voice communication, we are using the MCPTT or MCX server. This MCX server is based on 3GPP standards, which provides the functionality of voice as well as data, like one-to-many calls, push to talk, push to video, your instant messaging, your chat. All these are provided by this group communication solution here, that is MCX server. Now how the call will happen. So on the left, you will see this red connection. So this red line is basically from UE. These are the user devices. They initiate a call. As I mentioned, all the bearer will go to the S gateway. So the bearer will reach this S gateway. Now from this S gateway to the packet gateway, and packet gateway is connected to your external world through this SGI interface. Now data will reach to this group communication server. It's an external application basically, which provides the voice services, and the data will come back to the respective user in yellow line basically. Now if you want to talk to other systems like PA system also or IPPVX, this connectivity is possible through this group communication server through the call bridge server. So this is nothing. This is basically a SIP server. Call bridge server is a SIP server. So your IPPAVX through the SIP protocol or your PA system through the SIP connectivity can be connected to this call bridge server. So this PA system can also make a call to the LTE radio or LTE devices, as well as you can make a call through the landline also through this IPPVX to the call bridge server to the LTE user device. So this type of connectivity or features are also possible in LTE. So voice services are always through the application clients. What's our next slide? Now this slide we prepare for the ETCS level 2, that is a European train controlling system. Basically that is the signaling they are using as of now, ETCS level 2 and LTE. So ETCS signal is nothing, it's just a bearer for me, it's a packet for me. So in this slide, you will see again the same EPC components are there, the HSS, MME, etc. are there. These are at one location and connected to a SIP core, whereas on the through packet gateway, this ETCS server is connected. So ETCS server is nothing, it's like a application server. Similarly for TCAS also, I will cover that in next slide also. The TCAS is nothing, it's just an application server for me. Now on the loco side, you will see there is a OBU, that is onboard unit. So this onboard unit is of signaling system. So this signaling system, this will collect the data, the signaling data ETCS2, and there is also a OBU from my LTE. So when I'm saying OBU is nothing, it's a LTE modem or a LTE user device. So OBU of signaling system will pass on the information to my OBU, LTE OBU, and through air interface, basically this data will reach to the eNode B. First, I'll just press one button. Yes. Now this eNode B will pass the data to S gateway, P gateway, and this reaches to the SIP core. Press the next button. So now from this SIP core, I will decide, okay, this packet is intended for the ETCS server. So now here you will see the same call setup is there from the OBU, LTE modem, from the loco through air interface. The data it sends like movement authority or position report, all this information, whichever is there in the ETCS OBU, they will pass on that information to the LTE OBU. From there, through air interface, which is eNode B, then S gateway, packet gateway, and from here this ETCS PDN will go to the ETCS server, and vice versa. So this is how this information will go to the ETCS server and comes back. Now, what is the difference? What LTE is doing? LTE is providing a very high throughput, low latency. Low latency when I'm saying 10 milliseconds. There are other communication, like maybe voice call is happening in the system, maybe a user is talking to other users, and different applications or different throughputs, like maybe somebody is assessing the CCTV, etc. Somebody is making a video call. Now there are different packets are coming to this particular different users. Now what this network will do, it will always prioritize and give a highest priority to the ETCS data, because this is the most critical data which needs to its respective destination, that is ETCS server. So this the QCI is basically is defined for these packets or this application data. So it will always have the highest priority, and whenever there's a multiple packets enter into the system or it is this enode B, it will identify, okay, this packet is having the highest priority. I need to send this packet on the priority basis to its respective servers. So this is how we can define and treat different packets in the system. What's up? Next slide, please. Pass on the slides. I think let's go to the next slide. Okay, so this is about the TCAS. Earlier we about the ETCS. Now, what is the difference between TCAS and ETCS? So ETCS, what happened? ETCS is kind of a centralized system. When I'm saying centralized, they don't have equipment at each station. They just have some equipment at the track and on the OBU, basically on the loco, and then they have a centralized server placed at one location. That is RBC basically. Whereas in TCAS, this train collision avoiding system, this they have a different architecture. They have a distributed architecture as compared to the centralized architecture. So in this, every station they are having a stationary TCAS server. So every station TCAS is going to place one server. And in train, they will also have a TCAS OBU. In the loco, they will have a TCAS OBU similar to the ETCS. ETCS is also having their own OBU, as well as LTE OBU is there. Similar LTE OBU was there in the ETCS also. OBU or loco wise is similar, whereas on the central location it's different. Now, what happened in TCAS? TCAS OBU is connected to my LTE OBU. And currently they are using a UHF radio. So this UHF radio, how it functions, this UHF radio transmit two frequencies, F0 and F1. So F0 frequency is transmitted for 15 millisecond, and then for the next 15 millisecond it transmit the F1 frequency, then again for the next 15 millisecond it transmit the F0 frequency. So in that F0 frequency, it transmits the signal which is intended for the other locos, nearby locos, you can say. So nearby locos will receive that F0 frequency and communicate with each other. Whereas that F1 frequency is intended for the stations. So stations meant when saying stationary UHF radio, which is there in the stations. So F1 frequency is received by the station, and then UHF radio pass on that information to the stationary TCAS server. And then stationary TCAS server further process it and pass on whatever the decision it take and pass on through the UHF radio back to the TCAS OBU via the LTE OBU. But sir, just presses out. So this is how it functions. So in TCAS, basically train is interacting with the nearby locos also, and interacting with the respective stationary TCAS also. So all UHF radios, like stationary UHF radio, every station they have some coverage area. Similarly, this TCAS OBU is also having some coverage area. So they will just communicate within that coverage area. This is how it functions. Now there's a one catch in this. Now when LTE is introduced, LTE is a centralized technology, whereas TCAS is a distributed technology. So that's why there comes a green color integration dispatcher in between. This is an extra module you will see as compared to the ETCS. Now the data, the TCAS PDN through the packet data gateway first reaches to this integration dispatcher. Now integration dispatcher, what it will do? It receives the data from the respective LTE OBU or TCAS OBU, basically you can say TCAS and LTE OBU, and then assess it. Okay, this particular data is for the TCAS server 1, stationary TCAS server 1. So it will send the information to the stationary TCAS server 1. If that is intended for another server, a stationary TCAS server, it will pass on that information to another stationary TCAS server. Parallelly, also this will send information to the centralized TMS also, train management system also. All the information it will pass on parallelly to the train management system also. So this is how this functions. So information from all the stationary TCAS server will come first to the integration dispatcher and then will go to the respective TCAS OBUs. So there is a mapping of like enode Vs or wayside equipment plus the stationary TCAS plus the LTE OBU is there in the integration dispatcher. So all this intelligence lies in this integration dispatcher. What's up? Next slide, please. Now this is about the redundancy and geo redundancy and dual radio core, you can say. So redundancy is very important, whether it's a local redundancy or a geo redundancy, because our understanding, this system is going to be used for mission critical applications like TCAS or ETCS, etc. So if anything fails, there is going to be a huge impact on the operation of the trains. Basically, I hope the train will stop, you can say, stop moving. So this has a huge impact. So what we propose, or what we offer, the equipment we offer is comes with a local redundancy also, as well as with the geographical redundancy also. The EPC can be placed at one location. Let's take example of Bihar. We are having one EPC in Patna. Then second EPC can be placed in another state also. Let's assume we can place it in Delhi also. This kind of architecture is possible irrespective of the distance. So two EPCs can be there, and these are act as a geographical redundant EPCs to each other. On a hot configuration also, hot set configuration also, and on the load sharing basis also. There are different configurations possible as per the requirement. So all the modules, basically, all the modules of this EPCs can be geographically redundant to each other. Now, this is basically based on the architecture we propose for NCRTC also. It's a cloud-based application. So in cloud-based, what's happen? All the virtual functions, basically. So these virtual functions also have a virtual kind of n+1 redundancy, local redundancy also. If any virtual function fails, there is always a +1 redundancy available at the local site also. Even that fails, then it will go to the respective geographical redundant site. So in NCRTC, we proposed architecture where there is one OCC, Operation Control Center, and there is also a BCC, Backup Control Center. The same replica of OCC equipment is there in the BCC also. So these are geographically redundant to each other. So one is going to be at one location. Second geographical redundant site is almost 50 kilometers away from the OCC, basically. And these are in a hot standby configuration. So if one fails, another will take up immediately within a 30 seconds of time frame. And second is also, we suggested a load sharing. Load sharing means both sides will be active. So like MME of OCC is also active, MME of BCC is also active. So the data comes from the wayside equipment or the eNodeBs, basically. So based on the load, it will go to both the MMEs. Like MME1 also, some of the data will go to the MME1, some of the data will go to the MME2 also, and then they will talk to the respective HSSs, which are always in the sync. So here you will see this database, both the database of main site as well as the redundant site are always in the sync. So anything happen, any update happen in the site 1 is always immediately it will sync to the site 2 and update the data in the site 2 also. So there are different ways and the configuration ways available. This is on the EPC side, basically, where on the radio side, it's more typical, basically. So go to the other side, next slide, WhatsApp. So radio side, what happened depend upon the number of frequencies. So if you have 2 frequencies, then the life become much easier and simpler. If you have only 1 frequency available, then life become more complex, which is currently the cases. So my understanding is DOT is giving just a 1 frequency slot of 5 megahertz to the railways. So here you see this is one site, RRH1 blue, RRS2 orange. So this is one location where we are having 2 redundant RRH, basically. So we have 2 ways to achieve the coverage redundancy. This is a wayside or equipment. Wayside, when I'm saying we are having a eNodeB or a tower near to any station we are having a tower, and on the top of tower we have antenna, and or at the below bottom, basically we have this equipment. This can be at the top of tower also and at the bottom of the tower also. Now we are having 2 radiating equipments, RRH1 and RRS2. These are the 2 eNodeBs, you can call it. So coverage, you will see there is one blue coverage and one orange coverage. The blue one coming from the RRH1, same is coming from the RRS2. So you have an overlap of coverage of 2, from 2 equipments. So if blue one fails, so even you have a coverage from the RRS2 is here, the orange coverage will always there. But in this scenario, you require a 2 frequency slot. WhatsApp just press the next button. Here, this is the blue coverage you see on the top, and then there's the orange coverage. So there is a 100% overlap of coverage is there. 100% overlap. If one of the equipment fails, even then the second will always a coverage is there, like either from an orange one or from the blue one. So this is a 100% coverage overlap configuration, you can say.
Mahipal, one thing, how much is the coverage for a E-Node B? If the tower is there, then how much is the coverage?
Sir, the coverage is very subjective. When I'm saying subjective, it depends upon the tower height also, it depends upon the radiating power also, it depends upon the clutter. Clutter, when I'm saying like what kind of clutter is there, any it's an open area, rural area, or buildings are there, or urban area or dense. Third is the throughput requirement, sir. So basically in GSM-R and LT, this is one of the major difference. In GSM-R, we actually do a RF simulation based on the coverage RF signal strength level. Whereas in LT, we actually plan or do a simulation based on the service requirement or throughput requirement. Throughput, when I'm saying the cell edge in GSM-R, we said, okay, cell edge, we required a minus 98 dB or minus 85 dBm of signal. Generally, we used to say like that. Whereas in LT, we always talk about throughput. Like in the cell edge, I just needed 2 Mbps of throughput downlink and 512 or 1 Mbps, you can say 1 Mbps for uplink. And this 1 Mbps or 2 Mbps is basically based on the your service requirement. When I'm saying services like for any voice call, you required 15 to 25 kbps of throughput. For any ETCS signal data, you need to send it. Like for ETCS is hardly 10 to 12 kbps of data. If I'm talking about a normal CCTV, you need a 1 Mbps. I am talking about a full HD CCTV, you require 2 Mbps to 3 Mbps, etc. So these are the different services, sir. So based on these services, you can define like what are the services you're looking for, and based on those services, what is the data throughput you required at the cell edge. So let's assume I assume I need one CCTV, 10 calls, all these. Through that, I assume I needed 2 Mbps of throughput at the cell edge for the downlink and 1 Mbps for the uplink. So theoretically, you can with a 30-meter tower with a 20-watt output, and for a suburban area, you can have a cell edge of 3 to 3.5 kilometer on one side. So total diameter of radius, total diameter you can say you have a 7 kilometer from the center location. So 3.5 kilometer on the left, 3.5 kilometer on the right side, approximately, sir.
Because I just asked this question because right now in whole of our GC we have got that tower for the GSM-R. So whether that will be sufficient or we will have to further augment or something like that.
I think, sir, whenever we will plan, we will try to use as much as existing towers possible. But yes, it all depends. Like it all depends. What is the data throughput you require, sir?
Yes.
Also, just for information, when I'm saying coverage in this slide, we are just depicting that. So data throughput requirement in this slide, you see from the tower 2.5 kilometer, the data is coming 3 Mbps. Right, sir? On the right also and left also, from the tower side, it's 3 Mbps. As we go far from 0.5 to 3.5, this is just a depiction. This is just a depiction.
Okay, means with the inter-station distance of 5 kilometers, we can have a coverage of 3 Mbps approximately.
Yes, sir. So I'm saying just you have a coverage even beyond that also. You have a coverage of 2 Mbps, then to 3.5 kilometer, and you 4.5 kilometer you go, you have a coverage of 1 Mbps. Now, sir, as I mentioned, services. So if suppose for full HD TV transmission, full HD CCTV transmission, you require 2 Mbps, right, sir? Just example, I'm giving you example. So 4.5 kilometer, you are not able to transmit that because you need 2 Mbps, right, sir? So you are only having 1 Mbps throughput here. So you are not able to transmit a full HD CCTV. However, like for a video call, you just required 512 kbps of data. You for voice call, you required 64 kbps of data or 50 kbps, you can say. So those services you can easily do at 4.5 kilometer also. So services you can depend upon the data throughput, whereas based on the services you actually define, like what is the throughput you require, so that we will define at the cell edge and we plan the RF simulation accordingly. So this is how, like 4.5 kilometer also, it doesn't mean the coverage ends there. It's like you are just getting 1 Mbps there. So if you go beyond 4-5 kilometer also, like 5 kilometer or 6 kilometer, you are getting a, let's assume you are getting a 100 kbps of throughput there. Even in that scenario, 6 kilometer away, you are able to make a voice call, or you are able to send a ETCS or TCAS data back to the application servers. So that is possible.
Yeah, it's now clear.
Okay, sir. So, what's up?
मैं पाल सर, मैं संदीप बोल रहा हूँ टेलीलिंक से.
हाँ संदीप जी, कैसे हैं?
बढ़िया. मैं ये पूछना चाह रहा था, सर ने जो ये ऑर्गेनाइज कराई है उसका मेन पर्पस था कि एग्जिस्टिंग जो उनका इंफ्रास्ट्रक्चर है उसके बेस लेके हम इस टेक्नोलॉजी को कैसे इनको हैंडओवर कर सकते हैं विद व्हाट बेटर अचीवमेंट्स एंड बेटर फैसिलिटीज. उस पे अगर आप थोड़ा कुछ बता पाए. और दूसरा ये कि जो आपने भी 1 Mbps 2 Mbps है, तो जो सर्विसेज जितनी भी हम LTE की देंगे उसके लिए बेयर मिनिमम कितनी Mbps पे सारी सर्विसेज हो सकती हैं, क्योंकि GSMR नेटवर्क स्टेशंस के डिस्टेंसेस तो ऑलमोस्ट सारे पता ही है हम लोगों को, तो उसको पर्सपेक्टिव में अगर आप कुछ बता पाए. थैंक यू.
वो तो महिपाल ने बताया. Yes, Mahipal, please go ahead.
Yes. So services actually, we both need to discuss with each other what are the services is required by ECR. Services like, all these CCTV or maybe the voice communication only or video communication, all these we need to talk to each other and then finalize it. So based on those services, WhatsApp, can you go to the next slide? The coverage, next. There is one RF slide. Yes, next slide. Yes, upper one. Go back. Yes, this slide. Now, this is just an illustration, but here how we plan it. So if you will say the service scenario modeling, how many trains will be in the same cell at the same time, like 4 trains we considered. So this is kind of like, we need to consider some examples. On the second blue box, you will see like MCPTT, I said, mission critical push to talk. So there are 4 users, 50 kbps and 4 for driver, etc. So I just consider some example: video streaming 1.2 Mbps and voice call 50 Mbps, 5 for staff, 1 Mbps with non-GVR data services, SIP signaling, etc. So is this just an example? Basically, these are the different services. And if I calculate those services, I just require 6.27 Mbps. This is just an illustration. I'm just giving services and an example is taken. So this is how I will do the RF plan. Now this 6.2 Mbps I will use for the cell calculation. So in this, the cell coverage maybe comes as 1 kilometer or 2 kilometer radially. However, I don't need all these services. What is the services I require? Like video streaming, maybe I don't require 4 video streaming. I just need a 1 video streaming. Let's assume I consider here 4. So that is the means the main culprit here, which is consuming most of the bandwidth. If I just consider 1 video streaming, then this becomes 1.2. Then my this will reduce by almost 3.6. So this become a 3 point something or 2 point something. That's it. So that's what I'm saying. And then I will plan my network on 2 Mbps. So this is how first I need to identify what are the services I am looking for and for how many users. Then based on I will calculate my cell edge throughput requirement, and then I will do the RF simulation. And on that RF simulation, I will have a coverage like cell range. This is a way of doing it. Now here what we will do, we can do a reverse engineering here, as we have an existing tower, right? So what we will do, we will have a data available, like existing towers are there, the tower height is available with us, and then what we will do, using this tower height and our equipment details, parameters, etc., we will just check what is the maximum coverage we are getting. So this maximum coverage between 2 sites means, suppose 2 towers are there and the distance between these 2 towers is around 10 kilometers. Now my cell range is kind of defined 5 kilometers here, right? So here what I will do, I will just let you know, like with 5 kilometers, I am getting this much of throughput. So this is a reverse engineering kind of. I'm assuming at 5 kilometers, I'm getting a 1 Mbps. So I will let you know, okay, in this 1 Mbps, my this services are possible. Now, just to give you one more, I will explain it further. 1 Mbps is the cell edge. When you are moving towards your site, your throughput or data throughput will increase. That's what I was trying to explain in that diagram basically. So 4.5 kilometer, as in that diagram you saw, like it's a 1 Mbps. 3.5 it's 2 Mbps. 3.5 kilometer, when you are away from 3.5 kilometer away from the site, the throughput was around 2 or 3 Mbps, whatever, in this diagram, right? So 2.5 kilometer is 3 Mbps. So as you go near to site, your data throughput will increase, your the speed will increase. So some services are possible around 2.5 kilometers, some are possible after within 3.5 kilometers, some are possible within 4.5 kilometers. So you need to understand what are the essential services you required and what are the fancy services that you can say, or non-essential service you can say, which are just used on case-to-case basis and as and when required. So these are two kind of services we like ECR need to understand and define, and based on them we will do the simulation and plan, use the existing infrastructure for that.
Good.
I hope it's clear.
Yeah.
Yes, sir. Yes, sir. Second thing, sir, the user subscriber radios will be different.
Subscriber radios you can use normal mobile phones also, but yes, the SIM should be from our end. That should SIM is containing the information of the infrastructure. And if you want to use the recommendation is to use a rugged mobiles basically, and some mobiles also comes with the hard press PTT buttons also. So suggestion is always to use a ruggedized phone. They have a better life and more ruggedized, I suggest.
Maipal, for this LTE-R, LTE for railways, when you say, then
Yeah.
like PSMR, we had some emergency services and there was some emergency button on the handset and something like that. So do we have that sort of feature for this LTE also? LTE for railways?
Yes. Yes, so LTE for railways, we have all these features. I explained like preemption is there, emergency is there. So it says more or less all the features which are there in GSMR are also available in LTE-R. So
In that case,
in this architecture,
then handset may be different then.
handset may be different, but the reason being yes. Here, what we are using a soft button instead of, because we're using a touch screen phone. So the GUI is basically, it's on the screen. So these buttons are there on the screen. So we don't need any hard buttons for the same. The
Okay.
emergency button, etc., are there on the screen itself.
Screen itself. Okay. So those can be simulated by software also.
Yes. So those are basic.
I just want
Yes,
to
sir.
know, can we use the existing power supply which we are using for DDU Pradhan Ghanta section?
Yes, you can use the existing power supplies also if it meets the the requirement of the E node B powers. You can use it. In fact, the power requirement is much less in E node B as compared to the BTS or GSMR. And the form factor, etc., is also very small as compared to the E node B or BTS or GSMR. So you can use that. You can use the power supplies. You can use the tower. What you cannot use, you can also use if you have like existing IP MPLS or that kind of network. So you can use that also. What you cannot use is some frequency dependent item, as well as frequency dependent item when I'm saying like antenna or cables. If those are not lie in the same band, then you cannot use it. Or the GSMR main equipment like MSC, BSC, those you cannot use.
Achha, Maipal, one
Or
more thing.
BTS.
This say EPC. If I talk about ECR, so do I need to
Yeah.
have a dedicated EPC for ECR, or there was some discussion regarding this? Ki only one or two EPC will be good enough for the whole of the Indian Railways?
Okay, there are different tiering of EPCs is possible. Like in this slide, you will see we have a different tiering possible. Like there we have a EPC that just consists of couple of servers. We don't need like 15-20 servers also. There's a couple of servers which can suffice the ECR requirement. This can support up to 500 node Bs. So plus different tiering, when say we have a mid size EPC also that can cater up to couple of, you can say, states like Bihar, Jharkhand, or Odisha, etc. These can be catered by just one mid-tier EPC also that can go up to 2000 node Bs. We have a EPC also available that can cater up to the pan India level also, that can support up to 2,56,000 of node Bs also, like which is there for operators. What operators are doing, just giving you an example of BSNL here. BSNL are having two EPCs. One is in their Aurangabad basically, another one is in Pune. One is also in as a backup they are using in Bangalore. So what they are doing through these EPCs, basically they are catering to the Gujarat subscriber, Maharashtra users, Kerala, Tamil Nadu, Karnataka, and Andhra Pradesh. All these users are basically just catered by all three EPCs only. So we have different tiering available with the same functions, same availability, and same you can say, there's nothing, only the capacity difference is there. Otherwise, functionality wise, they are more or less similar. So it depends. Like if ECR wants to have their own EPC, they want their own control, that is also possible. But yes, in that case, I'll just give you an example. If the train is moving from ECR to the near, you can say, our NFR, then if NFR is having own EPC and they are having their own EPC, then these EPCs need to be connected to each other, like the roaming functionality need to be established if train is moving from one zone to another zone and they want to have the same function. So roaming needs to be activated.
Okay, one more thing. Suppose I have got a single EPC for the whole of the Indian Railways. My primary target right now is to have TCAS integrated with this LTE. Okay. So as you had explained earlier, because now we will have some dispatcher for integration and something like that. So now for each station, TCAS will communicate with directly EPC.
Yes. So yes, what happened? Each TCAS is, when you're saying, there is also node B near to that TCAS also. Every station kind of. Yeah. So this node B is connected through the optical fiber back to the EPCs. So all node Bs are connected back to the EPCs. So how the data will flow, basically from the train side, a loco, basically the data will go to the nearest node B. Suppose that loco lies in the coverage area of node B1, then the data will go to the node B1. From there it will go to the EPC, and from EPC it will go to the dispatcher, integrated dispatcher, and from dispatcher it will come back to the this one, the stationary TCAS of station 1. Yes, and vice versa. So this is how the call will flow. And this integrated dispatcher can be localized also. Like if you want, ECR will have its own integrated dispatcher. That is also a recommended one. So they will have their own dispatcher, and that is connected through the EPC to the through the optical fiber to the EPC. But both ways are fine with us, basically. So if this integration dispatcher, the green color, you say this block, this can be have a customized also for ECR, and this can be common, can be used for whole India also. But yes, the location can be anywhere. Like even it is intended for ECR, this can be placed in the you can say wherever is EPC. So separate for the ECR, separate for other zones also. Like they all have a different integration dispatchers, but they can be placed anywhere in the network. So this is one of the beauty, or the you can say beauty of the IP network. So you can place your entities or network modules anywhere in the network.
Wherever you want.
It just MPLS.
It is also beauty. All the trains will be communicating to EPC. Again, EPC will be communicating to all the stationary TCAS through integration dispatcher. If we talk about pan India level, say TCAS is rolled out in all the railways, then that will be the.
Yes, it's like that. Then we, just to provide this functionality, integration dispatcher is required, and recommended or suggested, like every zone will have its own integration dispatcher.
Yeah. So this integration dispatcher, we can have it in our zone also, instead of EPC.
Yes. You can
But
have. You can have.
we can have, and only it will be connected to the EPC.
Yes.
Achha, just one question regarding these telephone operators. Now,
Yeah.
for these phone operators, the requirement of bandwidth, that like we were talking about the bandwidth of eNode B. So,
Yes.
since there are a lot of subscribers are there and a lot of applications are there, that this requirement must be very huge. So, are they having this eNode B so closely located or something? I mean, what they are doing? We don't find see so many antennas around.
Okay. So for them, it's different. Because currently, operators, when I'm talking, some of the operators are still using 2G, 3G, 4G also, simultaneously at one side. So the major difference between your net is going to be in your network and their network. They are having a higher number of frequencies, the first thing. For LTE also, like railway is going to get just a 5 megahertz, whereas operators, if you talk about a Airtel, I'll just give you example of Odisha. Odisha Airtel is having 6 frequency slots of 5 megahertz, means 30 megahertz of frequency is available with them. This is the first case. Second case, they always plan based on the capacity, because their subscribers are kind of dense in one area. For example, in any factory kind of area, or there's a one plant in Odisha, coal plant you can say, or any plant. So what happened in this plant, they have couple of sites. Let's assume in 10 kilometer square of area, they have 2 sites. But yes, their number of subscribers are very high in that 10 square kilometer area, maybe more than 500, 600 something. Whereas for ECR, this number of subscribers will be scattered all along the track, or mostly it's concentrated on the stations, right? Even at a station, they will not have a much higher number of subscribers, maybe 10, 20, not more than that. My understanding is, and that is also through 1 or 2. Yeah, so that is major difference. So for them, we always, operators is always planned on the capacity basis. So capacity plus, yes, the throughput. So that's the major difference.
Okay, please go ahead.
Yeah, I think this is covered. Yes, so we were here actually, though. Yes. So this is a again architecture, you can say, in a block diagrams. Here left you see this is LTE devices. These are normal mobile phones, ruggedized phones, etc., which should be Android based or 5 and above. And this is LTE infrastructure. The black color you will see, these are the eNode Bs basically on the track side. On this in a dotted box is LTE. So this is very simple architecture, and these eNode Bs are connected back to the LTE core through optical, microwave, or IP, MPLS, etc. And then there is a application servers. Like LTE dispatcher is one of the application servers. So all these are connected to this LTE core through the SCA2. This is a basic, very basic architecture. Minimum number of equipments are required. That's it.
In LTE, there is no BSC. The node Bs are directly connected to the core.
Correct. So number of units are very less. So it becomes the architecture become very much simpler as compared to 3G or 2G. So what's the next slide, please?
Yeah.
Yeah. So what this is about Nokia's portfolio. So we have end-to-end portfolio available for railway network. So it starts from the devices. So we have a partners available for the devices. Nokia does not manufacture devices, ruggedized devices basically. Normal mobile phones are okay, but ruggedized devices we have partner available from with those partners. We've done a testing, our testings and all those things happen. Those are tested or certified partners, you can say. Radio access is one of Nokia's main equipment. You can say Nokia is #1 across the globe in radio access. So in fact, through our Chennai factory also, which Bhatt Sahab has shown in the starting, we have almost dispatched more than 5 million of eNode Bs from this, for eNode B in fact, to across the globe. So this number of we already manufactured in India for 4G. And core network also, we have our own server, airframe server, and our own software for it. So these are Nokia's own equipments. And core network also, we are #1 in India, and globally also we are #1. So for radio access plus core networks, we in 4G we are #1 across the globe, and we have all the modules, all the softwares are from Nokia itself. Like some of our competitor, what they have some of the modules, whereas other modules they buy from or have a tie-up with other providers, maybe with Cisco or someone else, like someone is providing applications, etc. But it's not the case with Nokia. So we are having our own core network, and we are having a different tiering from enterprise to the mid tier to the pan India level also. So this different type of tiering is available. Scalability is available with Nokia, which is not the case with the other OEMs. Now OSS and automation, yes, we have network management available, that is automation zone is available, self-organizing networks, etc. Subscribers and device management applications softwares is available. We have NetAct, which manages, we have NSP, which manages the core part. And transport also, Nokia is having a full portfolio for transport, from microwave radios to the IP/MPLS network. So last year, from Nokia becomes the #1 in the IP/MPLS in India. So that was the rating given to us, thanks to the Alcatel-Lucent to portfolio for that. Security is also, we have our own products from NetGuard to the telco clouds application. So we have end-to-end user firewalls, etc., whichever is required for the network security. So these modules are also, these softwares as well as other solutions are also available. On top of it, all these are the products basically which are available, which is required to set up a complete LTE network. So Nokia is kind of a one-stop shop for all the products basically. On top of it, we have a professional services like consultant design for the RF and for implementation optimization. Thanks to the Nokia's manpower available in India. So one of the slide you saw, like we have a 16,000 plus manpower is available in India, which is kind of 1/4 of the Nokia's manpower. So thanks to that, we can prioritize services in India. We can give a specific treatment to Indian customers also. But yes, we have those professional services available with them. Now this is more about the radio access, basically the eNodeB part. So we have a different eNodeBs available with us. So on the extreme left, this is Flexi Multi-Radio 10 BTS. So this is a smallest form factor of eNodeB available. This smallest eNodeB is kind of, you can mount in a wall also, on the top of tower also. This is very small, URAC 19-inch standard 2 URAC size. That's it. This is very, very small. Yet capacity wise, it can transmit 36 frequencies simultaneously of 5 megahertz, 360 watt output power. So this is very, very powerful. Despite being of small size, this can transmit a very high power plus number of frequencies, and the configuration you can have, like 666 configuration is available of 10 megahertz per sector. So this much of capacity. One single eNodeB can 5,000 idle subscribers and 2,000 transmitting subscribers can be supported by one single eNodeB in one single cell. So this is very capacity wise is very effective. And these on the right side, you will see these are the RRH, basically remote radio head. So these are IP65 equipments. RRH also you can mount on the top of tower. So this RRH is also a radio transmitter of BTS basically. So this BTS comes in different configuration. This is smaller as compared to Flexi Multi-Radio 10 BTS. So you have 2T 2R configuration when I'm saying 2 transmit channels and 2 receiving, and also 4 transmit 4 receiving, as well as 8 transmit 8 receiving. So there are different configurations available in RRH also. Right side, you will see there's a AirScale RRH and AirScale outdoor system module. So these are basically again the remote radio head plus this is also the eNodeB. This eNodeB is basically 5G ready, you can say. So you can, through software, you can use the 4G also, and through the software you can use the 5G also. Now this Flexi Multi-Radio 10 BTS also, you can say this same form factor, same power amplifier, same hardware you can use for 2G also, 3G also, 4G also. These are the software driven radios basically. Same is the case with the AirScale also. If you want to use a FDD technology, you want to use a TDD technology, there is no need to change the hardware. If you want to use a 2G, 3G, 4G, no need to, or 5G, no need to change the hardware. The same hardware can be used, but only the software required for the respective technology. That's it. So these are software-driven radios also we call. So this is about the group communication for railways. So as we talk about secured push-to-talk and push-to-video application, so Nokia is having a group communication solution for voice, providing this MCX services, mission critical services. And in this this application client is going to be installed in these radios, as well as there is a LTE dispatcher console, which provides the management to the field staff. So all the calls will come to this dispatcher, and it during emergency you can deal using this dispatcher. You can deal with the field staff also. Dispatcher is nothing, you can call it a super user kind of thing. So there is a GUI which you can install on a laptop or any computer, etc., and can communicate to any user. And you can also assign priority to the dispatcher. So generally we assign a higher priority to the dispatcher. All calls, all video calls you can monitor, all audio calls also you can monitor, using the dispatcher also. We have covered. I think this we already covered. So that's it from my side. This is one of the slide about Nokia, which we actually proudly explain. So we have 30 plus years of railway experience and the most complete end-to-end portfolio and turnkey services. When I'm saying 30 plus years, yes, market leader with 21 GSMR network. Totally, we have more than 100 GSMR networks, but yes, we countrywide we just divided into 21 GSMR network. That is the highest by anyone. More than 80% of railway market share across the globe is with Nokia. So this slide is we need to update it. We have more than 100 plus mission critical railway networks deployed. Yes. Out of this, I want to highlight one of a feature here, the Bell Labs. I hope everybody heard of this Bell Labs. So Bell Labs is part of the Nokia's innovation technology. So this is based out of US, and this is Nokia's R&D center, one of the center. So Nokia is also awarded 9 Nobel Prizes for its innovation in technology. So Nokia is highly committed and committed to the highest compliancy standards and has a basic cyber solution. So this is one of a running lab which we have in the Germany, basically with the Siemens as well as with the DB Doshewan. So this is a running R&D lab for the future railway mobile communication system. So we have kind of like tested different technologies for the evolution towards FRMCS. So along with the Siemens and Doshewan, we have a running R&D lab available, which is kind of, you can say, go to different stations and do the testings. So I think that's it from my end. So if any questions, you can ask.
Acha, Mr. Mahipal, you were talking about this frequency, frequency 5 megahertz frequency band. Only one frequency band we have allotted. And
yes, in several
limitations. You were talking about some limitations. If we have 2 frequencies, yes, then frequency is easily achievable. Can you elaborate on that?
So, yeah, definitely, sir. So there are 2 types of coverage I mentioned, like one frequency, LT and GSMR, there is also one difference. So in GSMR, the frequency reuse is either 3 or 4 cells, right, sir? After 4 cells, you can reuse the frequency. Whereas in LT, you can use the same frequency in the adjacent cells also, next cell also. In the same E node B, you can transmit the same frequency in all the cells from the same E node B. So this is because of the orthogonality of the signal. So same frequency you can be used all along the network. Now, but sir, can you please go to those slides here, 36 and 37? Yes. So when I'm saying this kind of coverage redundancy, yes, in this I said there are RRH1 blue color and RRH2 blue color. So these 2 blue colors and orange color RRH is there. So they are transmitting the coverage which is of blue color and orange color. So blue color is transmitted, you need a 1 frequency, and for orange color you need a separate frequency. Maybe it's of 5 megahertz, maybe 10 megahertz, maybe 3 megahertz, whatever, as per LTE standard. But you need two different frequency slot to have a 100% coverage overlap of blue and orange. So this kind of redundancy, if you want, WhatsApp, can you press it? Yes, again. Yes, that's it. So back. Yes. So this orange and blue, this 100% coverage overlap you see on the top. So there's a coverage of 100% overlap. This is only possible if you have the two frequency slots. Now go to the next slide. Now this is the second I was explaining. Now in this you see there's a RRH1 only on one station. There is RRH2 on the adjacent station. So there are, like every station, you don't have two RRH. Okay. So here what happened, this RRH blue coverage is coming from station 1, whereas RRH2 orange coverage is coming from the another station. They are overlapping. However, they are overlapping, but not of the different frequencies. Can you press WhatsApp? So in this, what happened? So this blue is coming from adjacent side. So 1, 3, 5, those are transmitting blue, and 2, 4, 6 from the sides, they are transmitting orange. So in this you have an overlap available, but this is like not 100% overlap. But yes, this is another way of achieving the frequency. So single frequency, you can achieve the coverage overlap by this way. Suppose your blue one fails. In this condition, your blue RRH fails. Let's assume RRH3 fails. So what happened? This blue will go, even you have coverage from the orange. This is not 100% overlap, but still you are having a coverage from the orange one, or a vice versa. If any orange coverage fails, like RRH4 fails, then you have a coverage from the RRH3 and RRH5 from the blue one. So this kind of coverage overlap is also possible using a single frequency slot. So if you have two slots, then you have a 100% coverage overlap. If you have a single slot, then this kind of coverage overlap is possible. So NCRTC, basically they have a single slot. So we proposed and offered this kind of redundancy there. So adjacent coverage redundancy, we called it, not the same site overlap coverage redundancy. So this is the difference, sir.
Okay. And what about the normal antenna size you required? Tower size, tower height, you can say.
Tower height, yeah, tower height, sir, we will, based on the RF simulation and throughput requirement, we will decide like what is the tower height required.
But normally,
So this is also
normally 30 meter or 40 meter.
yes, normally we recommend 30 to 40 meter, yes. But if you have, like some places you have 50 meter available, definitely that's an added advantage. Higher the height and better is the coverage and data throughput, sir.
No, because in ECR we have 30 meter tower size available. That's why we are asking.
Okay.
Based on that.
Yes, so typically we recommend 30 meter and 40 meter, but yes, whatever are the existing resources like existing tower, etc., we will reuse them. So in your case, we need to do a reverse engineering. So whatever is available or available resources, we will try to accommodate them first, and then whatever extra is required, we will. So this is how we need to do a reverse engineering.
I mean, based on that throughput requirement, we can do the reverse engineering also.
Correct.
You see, primarily my immediate requirement is functioning of TCAS. But apart from the TCAS, in subsequently other onboard services will also be required. So what we plan,
yes,
must plan for that also.
Correct. Yes, TCAS is like the requirement is very minimum. It's hardly required 10 to 15 kbps of throughput. So, however, for other services, maybe voice and other services, you need a higher throughput. So based on all those your essential services, we will calculate what is the minimum throughput requirement.
Okay, and that will have to be worked out.
Yes.
Achha, Maipal, if I increase the power of the radio, then can we increase the distance and the throughput?
Yes, you can increase the distance and throughput, but however, recommended by DOT and WPC, You cannot transmit more than 20 watts. So that is the recommendation of the DOT. So maximum output power, or you can say EIRP, effective isolated radiated power, should not be more than 64 dBms.
My Palji, subscriber limitation is there.
Sorry? Sir, your voice actually is correct. Can you please repeat the question?
He is asking about subscriber. How many subscriber? I think you have told around 3,000, 4,000 subscriber.
Yes.
One
So that
node
is
can take.
correct. So one eNode you can have 2,000 to 5,000 subscribers. So at any point of time, one cell you are not going to that much of subscriber. But yes, eNode also this is about eNode. Whereas EPC we can dimension up to minimum, you can say start with a 1 lakh to 10 lakh, or even 1 CR also. That is not a challenge.
Achha, recently RDSO has issued a TAN for this LTE. Have you gone through that TAN?
Yes, sir. We have gone through that. In fact, we were helping DSA also for drafting that TAN. So we are just going to submit our
Comments.
for comments. So, yeah.
Achha, you have been.
When you were telling that you have got some work from the railways, have you got the complete work or just a supply of the equipments?
It's a complete work.
Okay.
That work through Deltel.
No, sir. For NCRTC, it's through NCRTC. So
Achha,
it's
achha.
like design. Yeah.
Okay. Kaushik.
Yeah, correct. No, correct.
So, Michael, can you tell what is the cost coming per kilometer, or just say the per node? What is the cost?
I think WhatsApp can answer that.
Sir, that depends upon the normally basically what are the applications, what is the total overall scope, and depending upon the different parameters.
Broadly, sir, roughly.
Roughly on the radio, if you can see, I think maybe around 50 to 60 lakh per kilometer type.
But sir, who will handle the licensing? What is the status of that?
For licensing.
Yeah, WPC clearance and CIFA clearance, etc.
Yeah, WPC.
Initially, the railway need to get the WPC, or rather the spectrum, at least to the in which under 500 or sorry 700 megahertz, 5 megahertz, which spots. So all those, the first allocation or the frequency need to be allocated to railways. Once the frequency is allocated, then thereafter to bring the radio equipment, we need to get the WPC clearance. So once the frequency is allocated and the spot is identified, then we need to apply for the WPC import license of the radio equipment. For the coordination of the WPC and coordination, so Nokia can support. Nowadays, it is all online applications. Once the sites are identified, then how many sites are there. So those things, details of the lat longs need to be uploaded onto the site. Then the import license will be allocated. And there will be the charges for this the spectrum and also for the import licenses that need to be borne by the railways, because this WPC and this spectrum will be allocated for the employer, not for the contractors. It will be in the name of railways.
And sir, where are you producing this equipment and what is the lead time, sir?
So as I mentioned earlier, these radio equipments are being manufactured in Chennai, and some of the servers are all because these airframe EPCs are outside, and software is all available by downloading. And normally the lead time depends upon the delivery requirement, and normally it is somewhere around 8 to 10 weeks, maximum 8 to 10 weeks, because hardware wise it is the same which is being deployed even in the other private operators. Only the specific software is being supplied for the railway functionalities. Other than that one, the normal hardware is the same like the other node Bs which are in the public operators network.
So, sir, if you are manufacturing Chennai, then import license will be for what?
The import license, because import license, some of the radio equipment need to be imported, because right now the 700 megahertz is not being used in India by any of the operators, and also it's not being manufactured in Chennai as a 700 megahertz. So right now it maybe have to be imported. If those import has to be made, then the WPC license is required. And also before emitting the any radios at the site, railway need to get the WPC clearance.
Right.
Even though you have the spectrum of 700 megahertz, to radiate at a particular site, you need to get a WPC clearance additionally.
Acha, have you deployed this LTE technology in India anywhere? This metro railway, DMRC, what is that technology?
That is Tetra, sir. In the railway segment, LTE is not been deployed till now. Only some trials has been made, and in Korea we have deployed LTE for the railways. But in India right now, LTE is not deployed in any of the railways, or rather in metros also. However, we are deploying this LTE in Dhaka Metro.
Acha, but still this LTE-R is specification are still being finalized.
Correct. Yes.
Yes, you can see that.
All the functionalities have not been incorporated, isn't it?
No, sir. The standard FRMCS is officially is not been announced, but the draft specification of FRMCS is available. They don't call it as LTE-R. LTE is one of the access technology which is being deployed under the FRMCS. FRMCS is a future railway mobile communication which can use either 4G or 5G.
So LTE-R is also going to be announced, or it will be like LTE only?
LTE only. So there is nothing called as LTR. It's because it's driven from the GSM-R word, but it's FRMCS.
Okay.
So the Delhi Merit you are doing with the Tetra.
Yeah, most of the metros, they have gone for the Tetra solution in India, but right now I think they are slowly, I think they may, when the bandwidth requirement comes up, I think they will go for LTE. For the LTE in India, spectrum is the main challenge. So if they getting spectrum is a challenge.
Right.
So just one question, that you were saying that you have backed the contract for Dhaka Metro. What are the timelines? I mean, how quickly you can install the system and commission the system?
Sir, most of the time normally takes for the readiness of the infrastructure and the tower and other outdoor work. The implementation of the radio network and the core is very fast. Normally in the public network, we do more than 2,000, 3,000 node Bs per day is for the Airtel Vodafone. So the railways and the metros requirement normally has the factory acceptance test, then the deliveries, then the readiness of the site is the majorly is taking a time. But in the Dhaka Metro, we have already delivered our radio equipments and the core equipment. The outdoor towers and other things are yet to be get ready, but it is expected in 2021.
Sir, work completion period should ideally be 6 months or 12 months.
It depends upon how many sites and what is the track length and how many which routes need to be deployed. Normally, if it is around 50, 60 sites, I think maybe a 1 year.
No, so for in our case, we are having the tower at all the stations, so that should shorten the time.
Exactly. So if the infra work is ready, then it will be much faster.
Yeah.
I mean, what is the timeline for designing part? Simulation and all?
It depends upon the survey sector. So whatever the input available, if we need to do a physical survey, then definitely it will take some time. So in present scenario, it will take some time. However, if data is available, we hardly need 2 weeks.
How much? 2 days?
2 weeks.
2 weeks.
2 weeks.
चलिए ठीक है.
So overall, it was a very good presentation. At least we got some insight into this LTE, and we could understand it.
One last question on a lighter note.
Yes, yes.
How this name LTE evolved?
Long-term evolution.
I hope, sir, something has been cleared about LT. How things are moving.
नहीं काफी clear हुआ.
I'm just saying how the name this got LTE.
Mahipal, you can throw some light why this name.
Long time to evolve this technology. That's why it is named long-term evolution. Mahipal, is it? This is the reason, na?
I don't know much. They called it long-term evolution. Yes.
Yes, it may be having the longer period also, that it will be going to stay for a long time.
Yeah.
Yes. So we should close it, sir.
Okay.
Any more question? Anybody?
Sir, if there is no question, I have some one request, sir, to PCST and CC sir, our AMC work is, we have done a lot of work on the ECR.
We have taught you in very details. We will be doing it after June.
Yeah. So just
but we will definitely clear it.
Okay.
yeah. So otherwise, I will thank for the ECR for giving us the opportunity, and it was a nice discussion. And I hope we have clarified a lot of the basics on the LTE, and looking forward to support.
Yeah, it's really good. It was really very useful, I must tell. At least I got some insight into this LTE.
CC sir, seriously sir, thank you very much. At least you initiated the thing, and we could organize the thing with the support of Nokia for you.
Yeah, it was quite interesting. We spent almost 2 hours.
Yes, yes, sir.
Very interesting, and we can go also extend, but we have some engagement. Okay.
Yes,
Anyway, thank you all. Thank you, sir, and thank you all the participants who have joined it. We should close
Thank
it
you
now.
so much. Thank you so much, and sorry for
Thank you, sir.
extending the
Yeah,
timeline.
thanks, everyone.
Everybody.
Thank you.